The next talk is by Margherita Disertori, and she will speak about the supersymmetric model for quantum diffusion in 3 dimensions.
Thank you. So, the model I'm going to talk about is a joint work with Martin Zirbauer and Tom Spencer. So, let's see if I can. Yeah, okay. So, first I will give a very quick overview about random matrices and the supersymmetric approach. And then I will explain you what is this model we are working on and why it should have quantum diffusion. So you probably know better than me. So the problem is we want to study the statistical properties of large matrices with random distributed elements. So typically we have a matrix and some probability distribution. And we want to study in the limit when the size of the matrix goes to infinity, the statistical properties of the eigenvalues, then correlation functions, largest eigenvalue, and so on, or the eigenvectors, and then you are asking if the eigenvectors are localized or extended. Or there are situations where you actually, you have some quantum field theory, and you are asking about the correlation function for the matrix elements. And then you might study, you have some the probability measure depends on some parameter, and you're asking analyticity properties in some parameters of this probability. So the applications are huge, both in physics and mathematics. In physics, they were initially used for study of energy levels of complex many-body systems, and more recently, they have a huge number of applications in mesoscopic physics, and that means disordered conductors and quantum chaos, and we heard a lot about that. And they also seem to apply in non-commutative quantum field theory, and this has to do with quantum gravity, string theory, and perhaps the quantum Hall effect. Now, in mathematics, they are connected to the zeros of the Riemann zeta function, but also to problems of random permutations, random tiling, and so on. And I'm sure I'm missing a lot of other examples. For what concerns the techniques, well, you have, in one case, your probability distribution has some symmetry. And you're actually asking for the statistics of the eigenvalues. Well, then in that case, you can, if you can integrate out, for instance, the unitary rotations, and you can get explicitly the probability distribution for the eigenvalues, well, then you can use a Riemann-Hilbert approach and orthogonal polynomials, and there is a big mathematical community working on that case. They get all possible informations on eigenvalues. And the typical situation is, where the probability distribution is like a trace of some polynomial in H. Now, in mesoscopic physics, this is not the case. The probability distribution typically doesn't have a rotation symmetry. And moreover, suppose you don't want information on the eigenvalues, but on the eigenvectors, then there is no use in finding the probability distribution for the eigenvalues. Well, in this case, there is no general technique, but supersymmetry is widely used. But you can use also moments, and you can get nice results, or field theory techniques. So I will just, the two most famous examples of systems that show a diffusive localized transition are random Schrödinger. So you have a discrete Laplacian plus diagonal disorder, or the random band matrix case. And if you take the easiest case, a self-adjoint matrix, then you can say that the matrix elements are independent Gaussian random variables with average 0 and covariance that depends on I and j. And actually, the covariance goes to 0 when the distance between I and j is bigger than some parameter w. So what you get is a matrix which elements are 0 outside a certain band centered around the diagonal. Now, these two systems seem to have the same spectral properties and the same localization diffusive properties. And the relation is that in this case, you expect diffusion, at least in 3 dimensions, for small lambda. And here, you expect diffusion for large w. So the relation is w, the parameter w is like 1 over lambda in random Schrödinger. So what do we expect for quantum diffusion? Well, first we have to introduce the Green's function. So we take the inverse of h and minus e, and if e is in the spectrum, we have to add a little imaginary part. And now in 3 dimensions, you expect that the average of the Green function square in absolute value behaves in this way. Rho is the density of states, and d is the diffusion constant. While in 1 and 2 dimensions, you expect localization, so the same quantity should decay exponentially. All right, now, since we do all our work with the supersymmetric approach, let's review quickly what this means. So we can summarize it in 3 steps. The first, we write whatever we want to study in terms of ratios of determinants. For instance, the Green function can be written as a ratio of 2 determinants. Now, once we have these, we have to take average of these ratios, and it's difficult. So we try to write this average in a more friendly way, so that it's more easy to study. And that's a change of representation. And now, if you do things in a smart way, in the new expression you get, you can do saddle analysis. Now, the last part is to make this saddle analysis rigorous. And that can be quite difficult from a mathematical point of view. Well, here I can go very quickly. So if you just use one ratio of determinants, you will get only information on the density of states. If you want more interesting information on localization, you need at least 2 ratios. And you need to use complex Z1 and Z2 on opposite sides of the imaginary axis, of the real axis. Now, more importantly, what is this change of representation? Well, basically, it's a set of algebraic operations involving fermionic and bosonic variables. And so we have a product of averages of determinants, and we want to do the average over H. Now, the matrix elements of H are independent random variables. So the probability is just a product of functions. So in the measure, the H, the different variables are totally decoupled. There is no interaction. The only the interaction is inside these determinants that mix all the H. So you are in a situation where the measure is factorized, but the interaction is all in the observable. Now, after doing all these operations involving supersymmetry, you end up with a new expression. Now, this time, your variables are little n by little n matrices, and you have one matrix for each lattice point. And now, the observable now depends on a function for a q on one lattice point. Typically, it will depend on a q on 1 or 2 lattice points and not more. So now the observable is quite localized. Now, where is the interaction? Well, it's in the measure. So the point is that now the q are strongly correlated. So basically, supersymmetry is moving the interaction from the observable to the measure. So now you can hope that since the q are strongly correlated, they will act together, and the integral will be concentrated around a saddle. Now, another nice feature is that you started with an integral over volume square variables, n square variables, and now you have a n by n matrix, little n by little n, for each lattice point. So you have n square volume variables, which is still big, but it's much less than before. So the main advantage is that you have less variables, and especially you can do a saddle analysis. And you have an additional advantage, which is the supersymmetry has inside some symmetries. And in particular, because of the supersymmetry, the Q measure is normalized to 1 automatically. Now, to see it, we have to go one step back. In this final formula, there are only bosons. There are no fermions. They have totally disappeared. We could totally forget how we get from here to there and just say, well, this is a new measure of bosonic variables. Now, if we go one step back, actually the true formula is in terms of matrices that contain both fermions and bosons. And only after integrating out the fermions, we get to this. Now, here, it's easier to see there are symmetries that mix fermions and bosons. And they have a lot of nice properties, like normalizing the measure to 1. Now, since this measure is normalized to 1, you might think this is still a probability measure. Unfortunately, this is not the case. Typically, the Q measure is not positive. And that's the main problem. So last part, we have to do a saddle analysis. So if you just take the saddle approximation, then you just replace in the observable the value of Q at the saddle. But if you want to make this rigorous, you need analytical tools. And that can be hard. So first thing you need, so you will break your variables in variables on parametrizing the saddle manifold, and then variables parametrizing the fluctuations around the saddle manifold. Now, the fluctuations should be massive modes, so they should decay very fast. So we should be able to control them by some small probability argument, but then we have a problem. Our volume goes to infinity, and the estimates might explode with the volume. So you need some kind of cluster expansion to control this. But it's possible. But then you have to integrate the variables on the saddle manifold. Now, on the saddle manifold, these are slow modes. They have no mass. So then, and you can't do a saddle approximation any longer. So either you do an exact integration if you're lucky enough, or if you have some convexity, you can use Braskamp-Debye inequalities, some convexity bounds. Or if you have some symmetries, you can use word identities. Now, putting these two pieces together is not difficult if the saddle is just reduced to a few points. And that's the case when you have the density of states. When you study the density of states, there is no problem. The saddle is not a manifold. And then your problem is just to control fluctuations around the saddle. When the saddle is a manifold, it's not so easy to control the two, to decouple massive and massless modes. So, of course, life is not easy, so all localization properties have to do with the case when the saddle is a manifold. Now, let's see what is the typical problem of integrating over a saddle manifold. So here you have the measure on the saddle manifold when we have a band matrix with a Gaussian measure. So typically you have an integral over Q and S. Q and S are bosonic variables. Q is parameterized by, it's a 2 by 2 matrix given by this expression, and Ti is in the SU 1, 1. So this is a hyperbolic non-compact symmetry group, while S is just vectors in R3 of size 1. So this is just the rotations. And in addition, you have some fermionic variables that couple these two sectors, Q and S. And if you integrate out this fermionic variable, you will end up with some determinant which is coupling Q and S in a highly non-local way. So now, what are the problems? First, this SU11 symmetry is not compact. And you have no mass, so it's very difficult. You have variables that go away to infinity, and you have no mass to control them. There is going to be a little regularization, and you would like to say that your bounds don't depend on the regularization. And second, the interaction is highly non-local. So it's difficult to apply renormalization techniques or other. And typically, the measure is not convex. So this is still hard. So we were looking for something a bit easier. So we went to this supersymmetric model for quantum diffusion that was proposed by Martin in 91. It's a vector model, so there are no matrices. But still, it comes from, you can find it starting with a model with matrices. You have to choose a certain number of determinants above and below. You take the average, and then in the sigma model approximation, you find these. Now, it's a bit easier, but it's still expected to have the same features of the exact supersymmetric model for random band matrices. And what are the main advantages? Well, the first thing is that after integrating out Grassmann variables, the measure is positive, which was the one thing that was missing in general. So then you can really talk about probability measure. And the second thing, very important, the symmetries inherited by the supersymmetry are easier to exploit, easier to see. And it was actually very difficult to see them directly in the original model. So that's a good candidate. Now, instead of starting already giving you the model fermions and so on, I will just give you what we have after integrating out the Grassmann variables. So we have a real positive measure, and the action for this measure depends only on one scalar field, Tj, and where we have one scalar field for each lattice point. And so here is the measure. Well, here we have the measure on the T, and here we have the action, which is given in terms of something in the exponential and this determinant. Beta is some large parameter, and epsilon is the regularization. Now, B is given by a kinetic term, except that you see this is a bit strange because you have this cosh of the gradient, and here you have a sum over nearest neighbors, and plus a regularization. And this matrix M is a positive quadratic form that depends on T, and I will show you later what it looks like. So what are the importance? So the measure is positive and is normalized to 1. So it's a probability measure. Second thing, if I take epsilon equal to 0, no regularization, the action depends only on gradients. It's not easy to see, even when I give you because it's on B, here it's easy because we have just gradients. Well, but then we have this determinant and this piece here. And actually it turns out that when you put the two together, this depends only on gradients. That is not automatic. And third thing, that's not a nice thing. This is the action is non-convex, so no convexity bounds. And it's highly non-local because of the determinant. So we are keeping some of the difficulties of the original model. Now, I have to give you now the observable. So the equivalent of studying the green function square is studying the inverse, the matrix M minus 1 computed between x and y multiplied by this weight. So that was the... All right, now I have to really give you the expression for M. So M is given by D, which is an elliptic operator, plus a diagonal regularization matrix. So the elliptic operator is easily given in terms as a quadratic form. So here it is. We have a sum over gradient square times a weight that depends on T. So if T is 0 everywhere, so this coefficient is just 1, well, D is just the Laplacian, discrete Laplacian. Now, unfortunately, if this T vary, well, then this means that we have different weights on the different edges of our lattice. Like if, if the T go to minus infinity, our D is going to 0. And well, this is just the regularization term. There's not much to say. It's just a diagonal matrix with matrix element exponential to the T. Now, since what we are studying is this object, actually this boils down to study a random walk in a random environment. Why? Because we are studying this operator, and if these weights are 1, this is just the Laplacian, which is the generator of the random walk. But the weights now depend on T, so T is our random variable. So we have random weights on each edge. And actually, since x and y here are fixed, we can put this this number, exponential tx minus t plus ty, inside the definition of t. So here, multiplied by this. So what we actually have is a random local conductance, which is given by this expression. Now, so here now you see that actually this thing depends only on gradients. Now, if the t are all constant, well, then the conductance is 1. And then d is just a Laplacian. But in general, the conductance could be very small. And so this means that our operator is not uniformly elliptic. And that's the main problem in bounding. So we have very unlikely situations where this A could be very small, and so the inverse of this matrix element could be extremely large. And we have to prove that these situations they do not really matter. So what are the results? Well, in one dimension, there is already a result by Dirbauer in one dimension, for localization in one dimension, that says that the green function is, oh, sorry, this is our operator. I forgot to correct it, but it's this. So our observable decays exponentially. Now, in 3 dimensions, you expect to have diffusion. So what you expect is that the observable is dominated by t equals 0. And when t is equal to 0, well, you just have the Laplacian plus epsilon. And when epsilon goes to 0, that's just the diffusion case. Now, what we can prove in 3 dimensions is that if beta is large and we are in a cube of side L containing the point where we are looking at, well, then the eigenfunctions are extended. Now, so actually what we prove is that the L4 norm of the eigenfunction goes to 0 as 1 over L cubed minus A. And to prove this, we actually look at the observable not between 2 points far away, but at the same point, G00. And we prove that this is something of order 1 as long as epsilon does not go to 0 faster than 1 over L cubed minus A, alpha. Now, the optimal result would be alpha equal to 0. If alpha is 0, this means that the eigenfunction is totally constant everywhere. The eigenfunction associated to the particular yeah, I mean, there is an energy here hidden.
The eigenfunction of what operator? That's, sorry, maybe
well, I had to, I mean, there is a way to connect the L4 norm to the average of the green function G00 in absolute value square. You can show that.
Only by analogy.
There is an analogy here. I mean, this is just, I mean, if you were looking at a band matrix.
I understand that.
Okay, I mean, this is just, I can't say that we are really looking at this because it's.
This is taking a jump in the sense of Yefyetov.
Good, now I understand.
Okay. So what is the idea of the proof? Well, first we have to show that the T fields actually are more or less constant. So you have to prove that the fluctuations are small. And now, so if the fields are constant, then you look at your observable, and it becomes just the Laplacian plus this regularization. But this regularization is not epsilon. It's epsilon times this exponential minus t. So you still have to do something to check what is the value of this t. Now you do saddle analysis, and in 1 and 2 dimension, you find that epsilon e minus t is actually a constant. So it's 1 over beta in 1D and exponential minus beta in 2D. So actually, the saddle analysis is telling you that you have a mass. So you have localization. You don't have extended states. In 3 dimensions, you find that the saddle is t at t equals 0. So here you have epsilon times 1. So here you have no mass. And so you do have, so you do have diffusion. Now, the main problem is to control the fluctuations. Now, in general, it's very hard because there is no convexity, there is no locality, and so it's difficult to do renormalization. Typically, to do renormalization, you need some Gaussian piece plus some perturbation, which should be short range if you want to control the renormalization group. And here you have nothing like that. And moreover, the operator, you have to study the inverse of this D, and this D is not uniformly elliptic. So you might think, well, I have no hope. Actually, the only thing we still have are the symmetries inherited from the supersymmetric structure. And because of these symmetries, we find some word identities, and using them, we can prove that the fluctuations are bounded. Now, it's difficult to see the symmetries directly on the measure for T, but it's easy to see them if you go back one step when you still had the fermions. So now I should show you where the model was coming from. So you start with a vector made of 3 bosons and 2 fermions, and you define an inner product like this way, which is also metric. And now, if you want to go to the, as you want to go to the saddle manifold, you need to put some constraint. And the constraint is to fix the scalar product between 2 vectors to be equal to -1, which means that Z depends on the other x, on the other variables. And now you see that the submanifold you get is parameterized by 2 bosons and 2 fermions. And now the action is given by a kinetic term plus as a regularization piece. And now, if you choose the good coordinates, which is these holospherical coordinates, so the action will take exactly the following form. We have the gradient piece I've shown you before, and the regularization piece I've shown you before. But then you have this S. This is a real scalar field again, and it appears in a Gaussian way. And you have the fermionic piece. C and C bar are fermionic fields, and they appear in a Gaussian way again. So you can integrate them out exactly, and what you get is the determinant. Now, this measure is invariant under symmetries that leave the scalar product and Z invariant. So let's see some examples. Now, first main example, well, if you do the integral over the action, this integral is exactly equal to 1. So you have a measure which is automatically normalized to 1. Now, and this is true for all values of beta and epsilon. And actually, you could put here a beta which is that depends on jj prime, and an epsilon that depends on j. And the integral is still 1. You can actually add other pieces that contain, you could add to your expression other pieces like other scalar products, and since these are invariant, well, then the average is still equal to 1. So actually I could add other S, a lot of S, X, Y, S, X prime, Y prime. I can add a huge amount of objects here, and as long as I have the invariance under the supersymmetry, my integral doesn't change. Now, one example is the following. You can show that the average of cosh of the gradient minus 1, this is exactly equal to 1/2 gxy, where gxy is defined, now I'm afraid I lost it, I lost it. It's my gxy. Here, it's defined here. So gxy is actually the inverse of m computed between delta x minus delta y. multiplied by this object. Now, if you look at the measure over T, there is no obvious reason why this identity should be true. It's just one of the magic relations you have from supersymmetry. And this is true for any pair X and Y. X and Y could be nearest neighbors, or they could be very far away, but this relation is still true. So, one of the key identities you can obtain from supersymmetry is the following. If you take the average of the hypercosh to the power m is going to be some large number of tx minus ty, and you multiply this by 1 minus m over beta times this object, this g. Actually, I'm forgetting some terms, but it doesn't matter. I'm a bit, it is not the exact formula. Now, this average is equal to 1. Now, if we could say that this object, gxy, was smaller than some constant, uniformly in T, so this is a, if we have a bound that is not a bound in average, but it's a pointwise bound on this object, well then, this parenthesis is bigger than 1 minus m over beta times this constant. And as long as this parenthesis is positive, we can move it on the other side, and we find that the cosh to the power m in average is bounded by this constant. Now, if we can prove such a bound, then we can prove that the probability that tx minus ty is big is extremely low. Because we can say that the probability, no way, okay, the probability that cosh tx minus ty is bigger than some number is certainly bounded by cosh tx minus ty divided by a to the power m. This characteristic function, this is the characteristic function saying, which is 0 if cosh is smaller than a, and is 1 if cosh is bigger than a. So I can certainly bound it by a function which is bigger than 1 when the cosh is bigger than a. So here I have the chi, and I'm bounding it by a function that is bigger than this chi. This is something that is positive when the cosh is smaller than a, so it's certainly bigger than 0. And this is certainly bigger than 1 in this region. But now, this is the cosh of tx minus ty divided by a to the m. If we can say that this average is bounded by a constant, well, then we have that this probability is bounded by 1 over a to the power n times some constant. And when m is large, this is telling us that we have a very small probability of having a large deviation. So basically, that's what we use all the time. Now, of course, I'm cheating because I'm assuming that I have proved that this function was bounded by a constant. And I don't know if this is the case. Well, actually, it turns out that the bound on gxy depends on the distance between x and y. Now, if x minus y are nearest neighbors, then it's always true. And you don't need to take any average. It's just pointwise true. Then gxy is smaller or equal than 1. And this is just a question of looking at properties of a Gaussian integral. Now, if x minus y is bigger than 1, so we don't have nearest neighbors, this is false in general. So I certainly can't go through this argument. Now, but it is true if I put some constraints on lower scale fluctuations. So if I say, well, let's suppose that I know already that fluctuations at scales less than L are small. So so that my gradients don't change. They are not big if I look at Tx minus Ty is smaller than, x minus y is smaller than L. Well, then you can show that with this constraint, Gxy is bounded. But that means that you can actually, in order to prove this bound, you have to insert these constraints on lower scales. And since this identity is true only because of supersymmetry, well, if you put here a function that ensures these constraints, this function must not break the supersymmetry. Otherwise, you have an expression which is nice, but it's not equal to 1. So this is not completely trivial. It means that you have to put your function as functions of some expression which is supersymmetric invariant. And so it will contain not only the cosh, but also some fermionic variables. And then you have to show that still you have something like that. And now you still have, now you manage to prove that the fluctuations are not big as long as you have constraints on lower scales. But that's not enough. You have to take away these constraints. And to do that, you have to do some inducting argument on scales. So you say, well, I proved this for small scales, then using this result, I will prove the same bound on larger scales. Well, so Gxy can be, since Gxy is a quadratic form on gradients, is delta x minus delta y on both sides, we can forget about the mass term. This is actually orthogonal to the zero mode. And so actually what we have to study is this quadratic form, where d tilde is exactly the quadratic form I've given you before, where here we have these local conductance. Now, we don't really need, so what we need is to have some constraints on these local conductance. Well, actually, we don't need to say that fluctuations at lower scales are all bounded by a constant. We can let them grow. They can actually grow slowly with the distance. And actually, the bound is they should actually not grow faster than the distance to some small power alpha. And this alpha is exactly the parameter that appears in the statement of the theorem. And the last important thing, well, you could be very scared if you think, well, I have to check that I have a huge volume and I have to check the local conductance on each edge of my volume. Then I could have a bad event which is very far away, and the corresponding entropy factor is huge because I have to choose where my bad event is. Well, actually, you don't need to look in the whole volume. When you look at a bad fluctuations between x and y, and you want to prove that this fluctuation is not big, all you have to check are the local fluctuations at lower scale in a region, some diamond containing x and y. So you don't really need to, you don't care what happens outside this region. So all you have to do is to check what happens in this region. And that's not such a big region, so you can control the entropy factor. Okay, so now what still we have to finish is to prove now that the green function actually really decays as it should as 1 over the Laplacian. But we should be able to do that. And now we expect for small beta in 3 dimensions to have localization. But we still don't know how to show that. And finally, we would like to use these ideas to study the band matrix model. And well, in that case, the fermionic term is more complicated. We have an additional sector. We have the boson-boson sector with this non-compact symmetry and the fermion-fermion sector with some compact symmetry. And we have to put the two together. And of course, the symmetries will be more complicated to exploit. And we have to see if the and the measure might not be positive. So there are a certain number of additional problems. And I think I will stop here.
So the talk is now open for discussion. Sasha?
Several questions, but there's one question is, you mentioned it at some point very quickly that in 1D and 2D, you say you get a mess, which I understand means that you get localization. And
Yeah, but it's not a proof. I mean, that was, suddenly was just suggesting. It was very, I mean, there is, you
no, my
have to prove
question
it.
was that normally to show localization in 2D, it's not that we see it immediately. Yeah? We get, say, the right RG, and we see that it flows towards strong coupling, and then we say it looks
Yeah.
like this localization. I guess it should be same here, or you have something, you have better arguments.
Well, we don't have a proof. It's just that doing the saddle analysis, the saddle seems to suggest that there is indeed a mass, but that's far from being. Then we don't know how to
So you
make
see-
anything
no,
rigorous of
that's-
this. We don't know how to prove that fluctuations are small, and moreover, if you look at the saddle approach, I mean, where is it? I lost it. Further, check. Where is the saddle? Here. So,
See, Margherita, you write proof.
oh, that's the problem. I
Everybody's
see. Yeah,
confused.
this
You
is
should
very
write
confusing. I'm sorry.
heuristic.
This part is really a heuristic part. It's not a proof. And actually, the truth is, this is misleading because in our theorem, we never use the saddle. We actually
This is
never
a
use the saddle at all.
observation by Tom Spencer that if you just do saddle analysis, you get something that's not entirely crazy. On the other hand, I don't think it can be extended to a proof.
You
I
see,
think it's how you say that to establish 2D localization here, you have to do much more than just a saddle analysis.
Yeah, that's what is surprising.
Exactly.
To me.
No,
So
there is
if
no-
you see 2D localization on the level of some
and you see
cell
here,
analysis would be, of course, marvelous.
you miss
No,
a factor 1 over epsilon.
It just turns out that if you do a naive saddle, you get sort of more or less what you expect to get.
I mean,
But
it's
of course
kind of
that's-
reassuring, but it doesn't mean that you have any. You see, you expect to have actually 1 over epsilon times,
Yeah.
but there is no 1 over epsilon, so clearly
Oh.
the saddle is not giving you really the correct result. It's just suggesting that, yeah, it seems to work. But
All right, there's a question back there. Luca?
About the partition function, but can you say something about the model behind?
you mean,
I mean, you gave a measure, you gave an
Yes.
action, but what is the vector model behind it?
oh, that was very quickly. I mean, if you don't want to know the physical origin, the vector model is given here. So you start from, you take a vector for each lattice point, and this vector has 3 bosonic components and 2 fermionic components. And on these, now you define this inner product, and you add this constraint, which is telling you that z has to be a function of x, y, chi bar. So now you're actually defining your action. You have an interval with an action, and well, basically a delta function saying you that you are on the saddle manifold. And now you say, well, now I have to parameterize my saddle manifold, and it turns out that if you choose the right coordinates, you end up with the action I've given you. That's the, if you want then where to know where it comes from, then it's longer.
But this action, is it supersymmetric? So can we see it how, if you do rotations in the superspace, is it invariant?
Yes.
Because it's not evident.
Well, you consider all the rotations. I mean, V has both bosonic and fermionic variables. You consider all the rotations mixing your variables that leave this scalar product invariant. And then
First
you
term
have
is the supertrace gradient q squared. Second one is the supertrace lambda q squared. Any more questions? Yeah?
Basically not a question, but I think that at one point it was a confusion, and maybe it's useful just to reiterate that this is, in some sense, this is nonlinear sigma model without appropriate microscopic operator with disorder for which you can consider wave functions and all that. It's just that it has all interesting symmetries in that, but it's not derived from, let's say, like the previous talk. It was some say operator with randomness from which you derive this model, but this is, as far as I understand, it was not the case. But it just was the model itself was given and autonomous, right?
Well, I can also derive this model. You just have to do some things that you would normally not do. Normally, you want to average just some Green's function, some product of
Yes.
Green's functions following.
That's what I meant.
And if you want that, you cannot get this model. However, if you say that you will put an extra weight in the form of a determinant or a ratio of determinants at different energies, and you play with that, you can actually derive, in the sense of Roche-Fetov, you can actually derive this model.
So it corresponds to this quasi-green function. They're just weighted
Yeah.
some ratios of determinant in this sense. Derivatives of
You do some
ratios.
strange
Okay.
weighting in the disorder measure of the disorder, and then you get this model.
In the measure of disorder. So it's disordered model was with some strange disorder then.
Well, you have to multiply with the determinant of the energy minus the Hamiltonian. You can think of that as of extra factors like this as being part of the fundamental measure that you work with.
Ah, okay. More or less. Thank you.
Maybe add to this. We looked at this model, which is very simple, say on a beta lens, and then it has exactly the same properties
For sure.
as sort of normal sigma models for localization. So I think it's very natural to expect that sort of all qualitative features here should be very natural first step to look at this.
Okay, if there are no more questions, then
Okay,
one last question.
just about 1D case. 1D case you can write transfer matrix. Did I understand correctly that you don't have proof for 1D either?
no, for 1D, yes.
For
Martin
1D.
has a proof using transfer matrix.
Okay, so let's have coffee, and please be back at 11:30 for the next